All right. Now, just like functions of one variable, we didn't just stop at first derivatives, did we? We went on to some second derivatives too. So let's talk about second derivatives in functions of two variables. All right, so for z equals f of x, y. The complication in this becomes, well, you know, we can do the partial with respect to x, or we can do the partial with respect to y. Well, when we go to second derivatives, we can do the partial with respect to x or y again, off of either one of our other partial derivatives. All right, so yeah, here's the deal. The second derivative, there's going to be four of them, because this one, f partial with respect to x, twice, I guess you might say there, is, well, it's the partial with respect to x, then done with, again, the partial with respect to x. But we could take that partial with respect to x and then do a partial with respect to y as a second derivative. So we could do a derivative off of x with respect to x, but do the partial with respect to y. So that'll be the partial with respect to x, but then we do that partial with respect to y. Well, we can do the same thing for the y, can't we? The partial with respect to y, we can do the partial with respect to y again. But we could also do the partial with respect to y, then do the partial with respect to x. So, anyway. Now another, we'll do an example of one here in a second. But another notation you might see is this. The partial second derivative with partial of both x's there. We can also do this way. If we use our notation, what we're saying here is we're doing the partial with respect to x of f, partial of with respect to x, and then we're doing that again, right? And so the second derivative, the second partial, that's how the notation kind of looks there. Yeah, just like in second derivatives, yeah. Now, if we do f of x, y, partial with respect to x and with respect to y, the second derivative, you still have the second power looking thing there. But down here, we're not doing with respect to x twice now. We're doing with respect to x, then with respect to y. So partial x, partial y is what they have it looking like. So anyway, that's kind of how these look with kind of the Leibniz notation. Just FYI. Okay. All right. Let's do some second partial derivatives here. Find the second order partial derivatives. And let's do f of xy equals, let's do it over here. F of xy equals x cosine y plus y e to the x. All right. Well, if we're doing the second order partial, just like if we're doing the second derivatives of a single variable function, we first of all need the first derivatives. And in this case, we need both first derivatives. We need the partial with respect to x, and we need the partial with respect to y. We'll play off of those. All right, so the partial with respect to x would be just cosine y plus y e to the x, right? Derivative that's 1, so you just have cosine y. Derivative of e to the x is e to the x, so you just have y e to the x. Partial with respect to y, the x is fixed, so this would be what? Negative x sine y? And this would be just e to the x. Okay. So you need those first order derivatives first. Now, what would the partial derivative with respect to x twice be? Well, that would be the partial with respect to x of this one, right? We've already got the, since it's f of x, partial with respect to x, and then do the partial with respect to x of that. I'm doing the partial of that, right? Okay. Well, that doesn't have an x in it, so it's just a constant. So it's 0, and then that's still just y e to the x. Okay. All right, what about partial with respect to xy? Well, again, we're doing the partial with respect to x first, and then we'll do the partial with respect to y of that. And so, again, we're using this one, right? But now we're doing the partial with respect to y of that. And so this is no longer just a constant, right? It's negative sine of y plus e to the x. Okay. All right. Now let's go to fyy. Partial with respect to y twice, I guess. All right. And so that's the partial with respect to y. Then do the partial with respect to y again. So that's partial with respect to y. So now I need to do the partial with respect to y again. All right, let's see. What would that be? The x is constant, so it'd just be minus x cosine y. And that's a constant, since I'm doing with respect to y again, so minus x cosine y. All right. F of xy, sorry, yx, we already did that one. Same deal, except partial with respect to y. Now I do the partial with respect to x of that. Partial with respect to y. Now I do the partial with respect to x. So now the y is constant, the x is fixed, the y is fixed, so the x is, I'm doing the derivative of, so that would be minus sine y. Derivative of x is 1. And e to the x is e to the x. So you got 4 second derivatives. Now, you might notice this. Look at these two. F of xy, sorry, f partial, those two partial, second order partial derivatives. What about them? They're the same. And usually that's not by coincidence. Those are usually the same thing. They are usually the same. It's called Clairaut's theorem. Yeah, it's in the book there. Proof of it. If fxy and partial derivatives f x f y f y x f x y are defined on a region containing AB, point AB, and those things are all continuous at AB, sorry. Then theorem states that second order derivatives, those second order derivatives, f of yx, f xy, partial derivatives, are equal. The only thing is, you got to have continuity, basically. All right. So let's do that. Let's verify conclusion of this theorem. For f of xy equals y sine. All right, so ultimately we want both of these, calculate both of these. But to do both of those, we need the first order partial derivatives. So the partial order with respect to x would be what? Y cosine xy? And then partial derivative with respect to y would be, I have to use a product rule. All right. Y times cosine xy plus sine of xy times the derivative of y, which is 1. All right, so f xy, partial derivative, xy would be, all right, so I'm doing this one, but with respect to y now, right? So that is a product rule, so it'll be y times the derivative of that would be negative sine xy plus, reverse that, cosine of xy times the derivative of y, so that's just 1. Right? Oh, I forgot something here. Did I forget something here? Yeah, I forgot my chain rule. That's what I forgot. Back to this one. Partial with respect to x, yeah, it's y times the cosine of xy, but then I have to do the chain rule. Right?
Oh, you have y.
Yeah.
Whatever it is.
So doing the partial with respect to x, so I've got to do the derivative of the inside, so that would be y. So it's y squared. Yeah. I better do that because it'll mess me up. All right, so the same thing here. This would be times a y, or times the x, because the derivative of the inside with respect to y would just be x. So it's xy cosine xy plus sine of xy. Okay, now let's try it. So the partial with respect to x, partial with respect to x again. No, that's not what I want. I could do that, but I'm wanting fxy. All right, partial. All right, so this with respect to y would be what? Y squared times the negative sine of xy times the derivative of the inside would be x, right? Yep. So it's negative xy squared sine of xy. Plus, then reverse that, cosine of xy times 2y. Okay, let's hope that other one works out. So we need that other one to look something like that. All right, so the other one's f of yx, so that would be partial derivative. So we're doing the derivative with respect to x of this. All right. So it's, yeah, so xy times the derivative of that would be negative sine xy. Then times the derivative of the inside with respect to x, it would be y, right? Hey, that's looking pretty good, isn't it? That's negative xy squared sine xy. Which is what I've got here. All right, then derivative of that with respect to x would be cosine of xy. Oh, I didn't finish that. All right, so then for this one, I've got, there's a little confused. I should have picked a, yeah, I could have picked a better one probably. All right, but anyway, all right, let's see. We did first time, all right, so reverse that, so it'd be cosine of xy times the derivative of xy with respect to x would just be y. Then I would do the derivative of that, which would be cosine of xy times the derivative of the inside would be y. And that's where it comes together because that's 2 y's cosine of x. Okay. Sometimes it works out where one's easier than the other, and that's where this really comes in handy. That one, they're both kind of monsters, but they are the same. But yeah, look at this one, for example. Say I've got f of xy equals xy plus e to the y over y squared plus 1. Well, if I want to know x, y, x, fyx, that's going to be hard. Because, notice, I would first of all need the partial with respect to y, and so I'm going to have to use quotient rule on that. However, since I know this is very much related to that, let's think about that. What is the partial with respect to x? That's just y. And then the partial with respect to x of then partial with respect to y would just be 1. So isn't that 1 too? So anyway, some interesting little sidebars there. So